Hi folks, welcome back to Physics with Captain Rod. Making this video here to provide an example of how to analyze one-dimensional motion where free fall is considered. So what we're looking at here, imagine we got this rocket here that starts here at the position I call position 1, and imagine the engines go off, and that rocket accelerates at about 15 meters per second. That's about 1.5 Gs for 20 seconds. After 20 seconds, the engines turn off, and that's going to be at position 2 here. And of course the rocket's going to be moving pretty good, so it would continue up quite a little ways here before it started coming back down. And what we're going to try to calculate here is this total height here that I'm going to call hmax. We're going to look for the total or maximum height achieved by that rocket. So I'm going to go ahead and start analyzing this. And if you've been watching or following me either in class or via my videos, you know that when it comes to analyzing motion, what I like to do is look at it graphically here. So I'm going to start by drawing a velocity graph for this rocket. And again, the velocity graph is nice because it's very easy. It's kind of a one-step process to get both acceleration and position information from it. Now, here at what I'm calling position 1 here, that's going to be my t equals 0. The rocket is not moving yet. Right, so the engines are fired, but it does not have a substantial velocity vector yet, so this thing's going to go through 0, 0. 20 seconds later on the graph, the rocket's going to have a reasonably substantial velocity. Now I can calculate that a couple different ways. One would just be this. I'm just going to write out, we know that acceleration is equal to delta v over delta t. I know that the acceleration is 15 meter per second. The delta t is 20 seconds. It's pretty easy to solve that for the delta v. I think we're going to get, what, 300 meters per second out of that? That's a delta v, not a delta x. So now we know at this point right here is the point 20 seconds, and this distance right here is 300 meters per second. And I'm going to go ahead and assume constant acceleration from time 1 to time 2. Okay, now the next thing that's going to occur from 20 seconds on, well, now the rocket's engine's off, right? It's ran out of fuel, or somebody just turned the boosters off or whatnot. So at this point now, it's basically a free fall particle. At this point, the velocity vector at position 2 points this way, and it's at 300 meters per second. At position 3 here, it's gotten as high as it's going to get, so at this point it's not going to be moving anymore. Now, I could kind of start my clock over and do a new, call this t equals 0, but I don't really see any reason to. I'm just going to come over here on my graph and say, okay, now my velocity is going to start dropping. And I'm kind of wondering, at what point here is the velocity going to be 0? So there's a couple ways to do that. I'm just going to start with this. Between 2 and 3, this thing's a free fall type of situation. So the acceleration is gravitational acceleration down, if we assume air drag and other forces are not relevant. So that means the slope of this line is negative 9.8 meters per second. So the slope, right, rise over run. So I'm dropping 300. I'm over some amount that I don't know. So I'm going to write this out, minus 300 meters per second over, and what I'm going to do is just give this a name. I'm going to call that delta t, because that's what it is, a change in time, is equal to negative 9.8 meters per second. And I'm going to take a moment here and calculate a value. So I get about 30.6 seconds out of that. Okay. All right, that means that this time here is about 50.6 seconds. And now I got enough information here to calculate the maximum height pretty easily, I believe. So what I'm going to do is break this into 2 parts. In green here, I'm going to call part 1. This area right here is going to give me the first displacement between 1 and 2. I'll do this in green. It's going to give me this displacement right there. And then I'll do this in red. This area is going to give me the second displacement. And then the total distance traveled will be the sum of the two. So I'll go ahead and write that out, and let's see, how about we call this, well, I guess I already called it hmax. Let's do that. Hmax is going to equal, okay, the green area, 1/2, the base is 20 seconds. I'm going to put NCU here for note consistent units. That's 20 seconds. And then the height was 300 meter per second. So that's going to give me the green area plus, now I'm going to add the red area here, 1/2 the base. Now keep in mind the base is this distance, and it isn't 20, and it's also not 50. That's the distance I call delta t. 30, I guess I'll carry that 0.6 along, but 30.6 times the height, also 300. And again, I'll just put the units outside. This will work out in meters. I'm going to go ahead and calculate a value. And I get a value of about 775.90 meters. So, other things we could calculate, but I'm not going to in this video. I want to keep this short. You know, this rocket ultimately is going to come back down and crash. We could calculate the total time of flight. I'm going to go ahead and save that for another video. I'm pushing 7 minutes now. I'll just save that for video too. So I hope that this video helped demonstrate how to analyze one-dimensional motion using graphical techniques and concepts of slope and area. Have a great day.